Similarity proofs. So we're looking to conduct triangle proofs with the use of angle-angle similarity, side-side-side similarity, and side-angle-side similarity. So it's a lot like triangle congruence proofs, except we're only proving that the two triangles are similar. So they have the same shape, but they're not necessarily the same size. So the first postulate we're going to use for these triangle similarity proofs is the angle-angle similarity postulate. And remember, this states that if you can prove that two pairs of angles in one triangle are congruent to two pairs of angles in the other triangle, then you can say that those two triangles are similar. So we need a pair of angles. So here we'd have a pair of angles S and M and a pair of angles R and L. By showing that they're congruent, we can say that the two triangles are similar. So let's see this with a proof of our own. Here we're given that RM is parallel to SN and RM is perpendicular to MS and SN is perpendicular to NT. We're asked in this case to prove that triangle RSM is similar to STN. So the first step here would be to restate the given. All right, so now that we've stated the given, we start applying some of the key ideas. Well, the first key idea I see is parallel. And in this case, when we look at the parallel lines RM and SN in this case, if we think of this line here as our transversal, what this tells us is that we have corresponding angles here and here. And when we learned in chapter 3 is that corresponding angles involving parallel lines are congruent. So the next step of this proof is going to be for us to state that. So we're going to say that angle MRS is congruent to angle NST. We can say this just because they're corresponding angles. Or we can say corresponding angles are congruent. All right, from there, the next piece of key information I see is that we have perpendicular lines. Well, perpendicular means that in this case, RM is going to be a right angle, or RMS, and in this case, SNT is also going to be a right angle, or in this case, angles M and angles N are both right angles. So we need to say this. And we say this through definition of perpendicular. From there, we can then state that the two right angles are congruent. So M and angle N are congruent, and this is just definition of right angles. And so at this point, if we look, we have two sets of angles in both triangles. So that means we can now state, in the last step here, the triangle RSM is similar to triangle STN by angle-angle similarity. The next theorem we're going to use to prove triangle similar is side-side-side similarity. And remember, this is basically saying that all three sets of sides, or all three pairs of sides between the two triangles are proportional. So if you compare the length of AB over QR, that should be equal to the same ratio of AC over QS as well as BC over RS. So the sides need to be proportional. So in this problem, they tell us that A bisects JK, and that point B bisects JL, and that AB over KL is equal to 1/2. And they asked us to prove that triangle JKL and triangle JAB are similar. So we start by restating our given. All right, and so now that we've done that, we need to look at the term bisect. And so in this case, bisect is to cut something into two equal parts. Or essentially, you're cutting something larger into two halves. So if we approach that reasoning, so in this case, if we think carefully about the lines being bisected, so A bisecting JK and B bisecting JL, we should recognize that there's a relationship here, or looking at the length of, or noticing that the length of JA is half the size of JK, and the length of JB is half the size of JL. Because in this case, we're comparing triangles JKL and JAB, which is the smaller triangle to the left and the large entire triangle. So what we're going to do is we're going to state this in a way that shows that they're proportional, or they have some kind of relationship. So to do that, we're going to say that JA's entire length is equal to half of JK. We can also at the same time say that JB's length is equal to half of JL's. And we know that this to be true because of the definition of segment bisector, or definition of bisector. When something bisects something, it cuts it into two equal parts, so that one part of it is half the length of the entire thing. All right, with this, we want to make this look like a ratio, kind of like what we see here. Well, to do that, we have to essentially divide, in the first quantity here, we need to divide both sides of this problem by JK. So we end up with JA over JK equals 1/2. In the second quantity, we want to divide both of those sides by JL. And now we've shown that in both cases, the ratio is the same as the ratio for the first side pair we were given. And we were able to do all of the division there through the division property that we learned in Chapter 2. Now, just for continuity's sake, we're going to bring all this together. So we're going to take JA over, JA over JK, there we go, equals JB over JL, which equals AB over KL. And we're able to do all of this kind of between a mix of the transitive property as well as substitution. So we'll say transitive / substitution here. And so what's happened is, since we knew that all of the ratios were equal to 1/2, we went ahead and just set them equal to each other to show that all of the sides were proportional. Because right now we're trying to show that the sides of JAB, triangle JAB, are proportional to those of JKL. And we've done that. So the last step of our proof here, since we know that all the sides are proportional, is to state that triangle JKL is similar to triangle JAB by side, side, side similarity. The last proof property we want to work with here is side angle side similarity theorem. And so this time it states that we're going to have one pair of congruent angles between the two triangles, but we're also going to be able to show that the two sides that include that angle within the two triangles are proportional. So in this case, AB over QR is the same ratio as AC over QS, and then A and Q are congruent. So this time we're given that PQ is equal to 3/4 of PR and PT is equal to 3/4 of PS. And we've been asked to prove that PQT is similar to PRS. So the first thing we do is we restate our given. Once again, we want to show proportionality amongst the sides, and we can do that simply by dividing both of these particular problem sets here by values on the right. So in this case, I'm going to divide both of, in the first pair, both of the sides by PR to create my ratio. So that means I'll get PQ divided by PR equals 3/4. So there's my ratio. In the other quantity, I want to divide both of those by PS. So PT divided by PS equals 3/4. So now I've shown that the two side pairs are proportional. And I did this through the division property. Or they have the same ratio. To show that they're proportional, I'm just going to take the fact that since they're both equal to 3/4, I'm going to go ahead and set the two ratios themselves equal to each other. So PQ over PR equals PT over PS. And this can be done through the transitive property or substitution in this case. All right, now that I've shown that the sides are proportional, I'm going to look and find a congruent angle because I'm trying to use side angle side here. Well, I should notice right away that angle P should be congruent to itself because it's a part of both triangles. So angle P, congruent to angle P, and I know this by the reflexive property. And so right now I've shown that the two sides and the included angle all match the properties we need. The sides are proportional and the included angles are congruent. So that means we're on the final step of our proof. Triangle PQT is similar to triangle PRS, in this case by side, angle, side, similarity.